Welcome back to another session on physical sciences. We will focus on chemistry again today, and we're going back to rates of reactions. This time we will look at rates of reactions and the graphs for the rates of reactions. When we look at the concept map here, we did all the macro views and we looked at the micro view. But what we're going to do today is we're going to link everything back into using the graphs and to show us how the graphs of these reactions will look. I just want to grab a pen here quickly. So we're going to focus on the graphs for the entire lesson today. Now when we look at rates of reactions and we look at the graphs that we will look at here, there are 4 different types of graphs that we can talk about. Firstly, we have the energy profile graphs where we know and we can remember we have the exothermic and the endothermic graphs. Exo and endothermic graphs. We also have the graphs that we draw because of experimental data. These graphs will now be the typical, your rate is equal to your minus change in mass over your delta T. Then we will look at the rate of reaction versus time. In other words, not what changes, but the rate over time. And the last type will be the Maxwell-Boltzmann distribution curve. And this Maxwell-Boltzmann distribution curve, we will link that back to the collision theory where we look at a microscopic level of the particles here. So we will link this to the collision theory as we've done in a previous session. So terminology to keep in mind here is the activation energy. We remember what we said, the activation energy is the minimum energy needed for a reaction to take place. I just want to show it on a profile again. It's this energy that we need for that reaction to take place. Another term that we need to remember is exothermic profile. Exothermic meaning our energy is given off and we have a graph where we have less energy for the products and more energy for the reactants. Then we also have another term, endothermic. Endothermic reaction is where more energy is absorbed during the breaking of the bonds compared to the making of the new bonds. And then the last term that we've heard about a lot, and we spoke about it a lot at length in the last sessions, that is catalyst. We know that we have a positive catalyst, and that one is the one that lowers the activation energy. And we have a negative catalyst, which we don't work with, but that one will increase the activation energy, and it will slow down the reaction. When we look at the energy profiles, the first one that we have here is our exothermic reaction. And I want to remind you that your exothermic reaction, as per earlier studies, you know that it's the reaction where your reactants absorb more of your energy, and the energy that's absorbed is normally less than the energy that is released. So exothermic reactions will always release to the environment, meaning it gives off a lot of heat. And this is a type of graph for explosions, a type of graph for combustion of fuels. When we look at the next one, we will look at the endothermic reaction. Remember, we spoke last time about our slow reactions, where we need more energy to be absorbed to break the bonds. And this actually means that we have a bigger activation energy, but the energy being released to the surroundings is then less than the energy needed by the bonds. When we look at we can use any energy profile here, but I just want us to remember that when a catalyst is at stake, a catalyst normally lowers our activation energy. And when that activation energy is lowered, we saw last time that it actually provides an alternative path for the products to form. It's actually a faster path if you think if you do that, you can see that it all happens faster. So a catalyst, a positive catalyst, as we know, actually increases the rate of the reaction. The next type of graph that I would like us to look at is the rate graphs. And these rate graphs, if we look at the mass over reactants graph, this one I would like to explain further. As we look at the zinc and the hydrochloric acid, we can see here we start with a mass. The mass gets lower and lower, and we get to a point where it is parallel to the time axis. At this point, I said last time that the mass remains the same, so there's no more a decrease in the mass, and then we can use that to calculate the rate, and we said that that rate is then equal to minus the change in the mass over delta T. When we look at the next one, we have the volume of a gas versus time. And for this one, we can see in the beginning, it's a fast reaction because there's a lot of reactant to react, and it slows down until it gets to a point where it's actually parallel to the time axis. And at this point, we actually have an end of a reaction, and it basically means that the reaction has now stopped for some or the other reason. These are the types of graphs that we will look at in our discussion. So the question that I can ask is, if I do an investigation, it's carried out to measure the rate of the reaction between zinc and hydrochloric acid, and in this case we have hydrogen gas being released. The hydrogen is not just released, it's collected in a gas syringe. When we look at the questions in front of us, we have three curves, experiment 1, 2, and 3. And now for the questions. Indicate on the graph the time at which the reactions are completed. Now, we know that the reactions are completed as soon as we see parallel lines to the time axis. In which experiment is the rate the highest? Now, how do we know a high rate? A high rate we can always see by looking at the steepness of our gradient. It's normally steepest just after the start. So in experiment 3, we have the highest rate of the reaction. In which experiment is the yield the lowest? Now, the yield is what is formed during the experiment. If you look at experiment 1, 2, and 3, we can see in experiment 1, there's less product that's formed, but that is obviously because the reactants that were put in were less. And in which experiment is the temperature the highest? Now we know a higher temperature will lead to a steeper graph, meaning a faster reaction. Therefore, we can say experiment 3 is actually the one at a higher temperature. Another type of graph that we're going to look at using experimental data, we will go look at the volume of the gas versus time. Now, if you can remember, we used the conical flask with the reactant in it. We had a rubber stopper and we caught up all the gas in the gas syringe and took readings over regular time periods. A graph for that will look like this. At the beginning, we will have a steeper graph, meaning it is a faster reaction. And a faster reaction happens because there is a lot of product that react with each other. Over time, it becomes less steep, meaning it starts to slow down as we start to use up the reactant. At the end, we have a parallel line to your time axis, and that parallel line to the time axis is actually an indication of your reaction that stopped. Just remember, when your reaction stops, when it's a one-way reaction where the reactants form product, it basically just means that one of our reactants is used up. It can be both, but mostly it's one of the reactants, and it's normally the reactant that is limiting that will be used up. And that will end the entire reaction, because with one reaction short, we cannot have the same product. I would like us to go over and discuss a question now. Right. An investigation is carried out to measure the rate of the reaction, and the reaction happens between zinc, which is a solid, and hydrochloric acid that is in solution. The reaction is represented by the following balanced chemical reaction. Now, as you can see, the zinc, solid zinc, and the hydrochloric acid will form hydrogen gas that will be released during the reaction. But they tell us here that the hydrogen gas is caught up in a syringe. So just to refresh your memory again, this is where we will have to take note of the hydrogen gas over regular periods, how the volume increases with every time interval. Right, so the graphs will look like that. They've got 3 different experiments. Just remember, all these 3 experiments is a representation of having zinc and hydrochloric acid that reacts. The first question here is, indicate on the graph the time at which the reactions are complete. Now, whenever we have a graph, whenever we have a volume versus time graph or a mass versus time graph, you must remember that the reaction, the end of the reaction is represented by a parallel line. So the line that's parallel to the time axis actually indicates that your volume remains the same for a period of time. So indicate on the graph the time at which the reactions are completed. I would say it's more or less at that time that that reaction is completed. And if somebody would ask me, why do I say that? Then you can say it is the time that the curve flattened down, and it's not just flattening down, it's also now parallel to the time axis. The next question, in which experiment is the rate the highest? Now again, when we look at highest rate or lowest rate, if we have a graph, the thing that we're looking at is we look at the gradient of the graph. Now, if you go look at the gradient, when you talk about a high rate, your gradient will normally be at its steepest. And if it's not so steep, you know that the rate is declining. So if we look at this case, experiment 3 and 2, you can see, and experiment 1, the one with the highest rate is the one with the more steeper start to it. So I would say experiment 3 is the one with the highest rate. If we look at in which experiment is the yield the lowest, and suggest the reason why that will happen. If you look at these experiments, you know by the time that it flattened off, we know that no more product will be formed. So when we have a flattened off curve, we will have to go look at how much was put in, because the amount of reactant that is put in will determine the yield of an experiment. So in the case where we see experiment 3 and experiment 2, you can see the same amount of reactant has been put in. But for experiment 1, we can see that less reactant was put in, and it actually has a lower yield than the experiment 2 and experiment 3. So why would I say it's a lower yield? For experiment 1, I can see that there is less reactants that reacted over the time. When we look at our next question, just before we go on, remember when we have rate graphs, we always need to go look at the steepness of our gradient. And the other thing that we need to look at is wherever our lines is parallel to our time axis. So, in which of these experiments was the temperature the highest? And you must suggest a reason why. Now, if you look at experiment 2 and 3, you can see we started with the same reactants and we ended with the same product. But because experiment 3 is much steeper in the beginning compared to the experiment 2, we can see the experiment 3 will obviously be at a higher temperature. How do we know that? because when we have a higher temperature, we have more collisions per second, more effective collisions per second, and we know it leads to a higher rate of reaction. And this brings us to the first break. Please go and enjoy. Welcome back to Physical Sciences. I hope you've enjoyed the break. We're going to go on with graphs. In the first session, we looked at the energy profile graphs. We looked at exo and endothermic reactions and the graphs. And we also looked at the rate graphs. So we looked at the graphs specifically from experiments where we looked at the volume over time graph, and we looked at the decline in our mass graph. So now we're going to take the time to look at in a deeper detail to the graphs that we get from experiments. Right. So from the experiments, we said there's 3 ways to measure our rate of reaction. We said it's to catch up the gas, so we can go look at the change in the volume of the gas over time intervals, regular time intervals. We can go look at the decrease of our mass over regular time intervals. And if you can remember back then, there was a third way that we can measure the rate of the reaction, and that was to look at the color change that we get, especially when we produced sulfur that made the whole solution a milky color because of the precipitate. So these are the experiments, or the experimental way to determine and to calculate the rate of reactions. So if we're going to go look at our first graph, and our first graph is all about the mass of the reactants versus the time. And I need to remind you that because of this decrease in mass, it actually means that we start off at a high mass, because at the beginning there is lots of reactant. So at the beginning we have a very fast rate, and that fast rate goes hand in hand with a very steep gradient. So when you look at it, you see the steep gradient, and then as the reaction goes on and the reactants are being used up, there's less and less reactants, therefore the gradient becomes less steep, and it happens because the reaction is now slowing down. The reaction is still happening, but it is slowing down, and it will go on until we get the parallel lines. And I said to you, if you have a parallel line to the time axis, that basically means that the reaction has stopped at that point. Now, when a reaction stops, one of our reactants, or it can be both of our reactants, is used up. But say, for instance, only one of our reactants are used up, it basically means the reactant cannot any further produce the same products. So at that point where the reactants are used up, we will have a parallel line, and you can actually read that from your axis, from your mass axis here. So when we look at this rate of the reaction, the rate at the decrease of the mass of our reactants, we can actually go and work it out mathematically by saying the rate of this reaction is actually equal to minus the change in the mass over the change in our time, over regular time periods. Now that negative, I just want to explain where that negative will fit in when we do the graph. Now, firstly, you need to remember that this gradient that we have here is actually the gradient that will actually be equal to the rate. So if we use the first graph where we look at the decrease of our mass, we can use that decrease of our mass, which becomes our gradient. We can actually use that now to draw a new graph, and that is the graph of the rate of the reaction versus the time that the reaction is on. So if you look at here, let's say we start there, we have an initial mass there. Let's say this is our final mass. So because our final mass is smaller than our initial mass, if we go plug that into our formula, we will have the rate being equal to minus a small number, small mass, minus a bigger number for mass, and that will be over our delta T. So our answer for the change in mass will then be a negative number, and that negative change in mass times the negative in front because of the decrease will then lead to a positive answer, a large positive number. So it's not just large, it's a large positive number that we have here. So if we want to go plot this on the graph of rate versus our time, we will say that first big number can be plotted as a significant number on my vertical axis or on my rate of reaction axis. If we go on and we go work out a tangent line of the gradient, maybe at that point, again we will have an initial mass and a final mass. So because the final mass is smaller, again, we will get a positive number, but the positive number will be a little bit smaller than the first number. So if we're going to do that over time, we will have a plotting point more or less there. And as we go on, we know that as we use the reactants up, we will later only have products. And that will stop the reaction as soon as one of my reactants are used up. So for the last one, where we have that part of the gradient, it will actually equal a 0, which means that we have a 0 point there on our graph. And if we do the line of best fit there, we will get a graph with a negative gradient. We want you to understand where that negative gradient comes from, how that negative in front of my expression is used, and how my mass is actually, the final mass minus the initial mass is actually always ending in a negative mass that we get, and that we plot on the rate graph, and the rate graph has got a negative gradient. Remember, the rate graph comes from the change in mass, that's negative, over the change in time. When we go on to the next one, where we look at the volume that's been caught up in a syringe over time, this is a positive, actually positive, because at the beginning we have a volume of 0. At the beginning we've got lots of reactants, so we know that it is a fast reaction. We know that it is a steeper gradient. So if we go look at our final volume versus our initial volume, we have a bigger volume minus a smaller volume, ending in a gradient that we can plot as well. When we go look at the plotting of this gradient, where we have a change in volume, we still sit with a bigger number, a little bit smaller number, and a number that actually is now equal to 0, as when we get there where the reaction more or less stopped because one of the reactants are used up, when we look at our delta V will be our final minus our initial volume, which will actually be equal to 0, meaning that at that time, with regular time intervals, we will at that time have a volume of 0. So if we go look at the plotting of this if we go look at this with an increase in volume, even though it is a positive rate expression, we will still see that we have a negative gradient starting from your high positive to your 0. Just look at the unit of the rate there. Because we were working with delta V over delta T, we were actually working with centimeters cubed over time, which is seconds, and our unit here will be centimeters cubed per second. We're about to take another break. Please have a sip of water or some coffee or tea. I'll see you soon. Welcome back to another session of Physical Sciences, and we will carry on with rates of reactions, specifically the graphs of rates of reactions. We are going to use this last session to talk about the graphs, but to link the graphs on a sub-micro level to the collision theory. So we will go look at the collision theory as we explain the graphs. The terminology for this part is, we should remember what temperature is. Remember, temperature is a measure of the kinetic energy of a substance. So if you have a high temperature, you always have a high kinetic energy, and a high kinetic energy actually means that the average speed of your particles will also be high. So we need to think in terms of the average speed of the particles, because we are now talking about particle level again, and we need to think in terms of the kinetic energy that goes hand in hand with our temperature. Up to now, we've looked at the energy profiles, which we know is the exo and endothermic profiles that we looked at. We looked at the graphs from our experiments, where we looked at a decrease in mass over the change in time. We also looked at the volume that we caught up in a syringe, how that volume increased over time until the end of our reaction. Then we used this experimental data to actually go and look at our rate of our reaction versus our time, and we saw that as your rate of reaction, as your reactants are converted into products, it actually shows a negative gradient. The last part that we're going to look at, as I said, and we will link this to a sub-micro level, where we look at the collision theory. So from now on, we're now going to talk about collisions again. And remember, we spoke about effective collisions and all the other things that goes with the sub-micro view. The distribution curve that we're going to use on a sub-micro level linked to the collision theory is the Maxwell-Boltzmann distribution curve. Now the curve looks like this, and as you can see, it shows all the particles and this is not just particles, this is actually our reactant particles that now moves. Remember, the particle theory says all matter is made up of particles, and these particles remain in constant motion, and that motion is determined by your temperature. So if we look at the normal distribution, normally it will look like this. We have particles that have almost zero energy, up to particles that will have a high energy, and then the particles that will actually reach this point where the energy, the kinetic energy, is actually bigger than or equal to my activation energy. The Maxwell-Boltzmann graph, like I said, we will link this to the collision theory, where we talk on a particle level. Firstly, we need to understand that it shows the distribution of the kinetic energy of particles. Remember that kinetic energy is a measure of the temperature of the substance, or what the substance is while this reaction is happening. It is used to explain the rate of a reaction. Just remember, this is a statistical curve, and we can then actually go and determine that we can say this is more or less how many of our particles have a low energy or a high energy, or the average energy of the curve. When we look at the curve, and this is a normal distribution under normal circumstances, on our vertical axis we have our number of particles, and on the x-axis or the horizontal axis we actually have the kinetic energy that is measured in joule. Now, remember what we said, for an effective collision there need to be two things that are met, two requirements. There must be a correct orientation, and except for the correct orientation, there must also be, our kinetic energy must be equal to or bigger than our activation energy. Right. So when we look at the normal distribution, you will see that most of our, on average, our particles lie in that segment. On average, that is also going to determine the peak of our distribution curve. Then if we look at the shape of the curve, this shape is, like I said, a normal curve, but this shape is at a certain temperature. So at this certain temperature, we have a lot of particles here, and all these particles move and collide, but only that part of the particles will have effective collisions, and that effective collisions lead to product. So if we look at this normal curve again, and on the normal curve, we will see we have about that sample of our particles that have a lower average temperature or a lower average kinetic energy. If we go further, we will see that we have a sample of our particles that will actually lean towards the average kinetic energy at a higher, slightly higher temperature. But what we need to understand is this whole curve has got particles in motion. These particles are colliding. All the particles on this side of the red line, to the left of my red line, are just moving and colliding, but they do not form effective collisions. It is only the collisions from this red line onward that are effective collisions, and these effective collisions lead to product formation. And that brings us to the point where we obviously deserve another break. Welcome back to another session of physical sciences. We're going to go on with the chemistry, and we're going to talk about the graphs, specifically linking our graphs to the collision theory on a particle level. We spoke about the Maxwell-Boltzmann normal distribution curve. We said last time that it's a statistical curve where we have some of our particles having a lower energy or lower kinetic energy, moving at a slower pace, as opposed to higher energy, higher average kinetic energy, and where we obviously have the peak in our graph. The question today is, why does an increase in temperature result in an increased rate of reaction? Now, when we first go look at the normal distribution, this is how it will normally look at a particular temperature, we see, as I said last time, this is all the particles, this particles is in motion, and this motion is determined by the temperature that these particles are exposed to. The part here is the particles that cause effective collisions. In other words, this part of my distribution curve is the particles that will form product because these particles form effective collisions. I just want to remind you again that an effective collision has got two requirements. Firstly, an activation energy that's smaller or equal to my kinetic energy. And secondly, there must be a correct orientation, meaning the electron pairs should overlap their orbitals with the correct other unpaired electrons. When we go back to the question of an increase in temperature, so if this is my particular temperature, let's say this is my normal curve. We know on the normal curve, it is the spread of all our particles at different kinetic energies starting from 0. So if we look at having, I just want to take this out, I think, so that we don't get confused there. If we look at the red curve there, this is a curve that happens at a higher temperature, at an increased temperature. Now what I want you to see here is the peak of my normal curve actually moved to the right and it moved lower down. Now why do we have a lower down peak? Why is the peak now a bit lower? You should remember that in this normal distribution, there is a number of particles. And in this distribution at a higher temperature, we still have the same number of particles. And these particles are actually now spread, sorry for that, these particles are actually now spread in this red curve that we see here. So what we can see now is our activation energy is actually now showing us that that compartment there is the compartment that will have effective collisions. So if we can explain that in terms of the collision theory, we can say at a higher temperature, we have the particles that move faster on average. The particles will collide more frequently, meaning they will bump more frequently. And if we have that bumping more frequently, we obviously have more collisions per unit time, but because that particle collisions is more per unit time, the likelihood of having effective collisions per unit time is very high. So we will have more effective collisions per unit time. And if we have more effective collisions per unit time, it actually means that the rate of the reaction is high. So if we look at the graph, we can now see, as I said before, that entire part there is the particles where there's more effective collisions that happened, and that part of my graph, more than before that it was only that part that was product, I have more product that is formed because there's now more of my particles that have effective collisions. When I look at the next question, a decrease in temperature results in decreased reaction. Why does this happen? Firstly, we need to see that T1 is now showing our normal curve, and T3 is showing our curve at a lower temperature. Now we know temperature is linked to the speed, and that speed is linked to the kinetic energy. So if we look at our distribution, we now see that from the normal curve, I have a higher peak, and my peak is more to the left. So it shows you now, on average, I have a lot of particles that has a smaller kinetic energy than the particles in the original curve that we have. So when we look at the more particles, we will see there is now more particles that will have effective collisions. So when we have a decrease in our temperature, we have more particles that on average has that kinetic energy. And if we look at our blue curve, only that part of the particles will actually result in product, because only that part of the particles will have effective collisions. That is why if we look at a decrease in energy, there's a decrease in the average kinetic energy, there's a decrease in speed, so we have less collisions, less colliding with each other, less effective collisions, and therefore we have a decreased rate of reaction. We're going to move on to the next factor that we can explain in terms of Maxwell-Boltzmann as well as the collision theory. Remember, your Maxwell-Boltzmann distribution graph is all about the kinetic energy of the particles. When we look at why does an increase in the concentration result in an increased rate of reaction? Firstly, I want to remind you that when we have an increase in concentration, according to C is equal to N over V, I said to you the last time that the concentration is directly proportional to the number of moles. So the concentration is your number of moles in a given volume. If the volume is kept constant and the concentration is increased, then it basically means you have a higher number of moles compared to the concentration before. So an increase of concentration leads to an increase in the number of moles. If we go back to the Maxwell-Boltzmann, I want to remind you again that this is our normal curve, our normal statistical curve, where we will have a peak where we have our average kinetic energy for most of our particles. But when we have an increase in concentration, I said that we now have an increase in the number of moles, so the number of particles are now more than before when we had a lower concentration. So you can see if you go look at the peak here, your curve is just now a little bit bigger than before. And that bigger curve is now because of the more number of moles, the more particles that we have under the graph, in the area of the graph. So an increase in our concentration led to an increase of the number of moles, and we can see that if we look at the curve that's now a bit bigger. But now when that curve was a bit bigger, the activation energy remained the same. And this part are all the effective collisions that we have. So if we look at an increase in concentration of the reactant, we said there will now be more reactant particles per unit volume. In other words, C is equal to N over V. We have a higher concentration, so we have the number of moles are more if our volume remain constant. So we now have more particles per unit time, more particles per unit volume, and that particles is colliding all the time because there's more in that small volume, and if there's more collisions per unit time, we have a likelihood of more effective collisions per unit time, and that effective collisions per unit time leads to a higher rate of reaction. Action is then faster. So we've now dealt with the Maxwell-Boltzmann graph, distribution graph, where we looked at an increase of temperature, a decrease in temperature, and we looked at an increase in the concentration. The next factor that we're going to look at on a submicro level is an increase or a decrease of surface area. So when we look at the surface area, we have why does an increase in surface area, and now I want to remind you again that an increase in surface area means finer powder, not chunks, more powder. Why does that result in an increase in the rate of the reaction? Now, just as a reminder, I've got the same photo as before. In the first case, we've got a lump, and in the second case, we made the lump finer into powder. Remember, the bigger the lump looks, the smaller the surface area, because the surface area is actually the contact area where our collisions take place. So when we look at a powder, there's more contact area. So for a powder, we have a larger surface area. So when we look at our Maxwell-Boltzmann graph, we will see that we have the normal graph. And because of the surface area that's now increased, we now have more particles or more interaction on the bigger surface area. So when we use powder, we actually now have more particles that interacts during the reaction. We have more particles that actually has that average kinetic energy. And if we go look at how many particles will actually result in effective collisions, we can see that entire part there result in effective collisions. So, with the collision theory, we can then now say an increase in surface area will increase the rate of the reaction, because the larger the surface area, this is the contact area, the more particles are involved in the collision. So more collisions per unit time, more effective collisions per unit time, and that leads to a higher rate of reaction. The next factor that we will look at is, why does an addition of a positive catalyst result in an increased rate of reaction? Right. Want to remind you that a positive catalyst is a substance that does not take part in the reaction, but it does speed up the reaction by lowering the activation energy. So if the activation energy is lowered, it basically means it is an alternative route that can be followed. So a positive catalyst lowers the activation energy of the reaction, and it provides an alternative route or an alternative path, meaning that product will be formed faster. Remember, not more product, just faster. So there will be more collisions per unit time. There will be more effective collisions per unit time, and that will lead to a faster rate of reaction. We go look at how the positive catalyst will be shown on the Maxwell-Boltzmann distribution. Remember, it lowers the activation energy. So if we go look at our axis here, our kinetic energy on the x-axis, we can now see that the activation energy now moves a little back on the axis to a smaller number. So all these particles there will result in effective collisions per unit time. Right. And in summary, we are now almost at the end of our lesson. I just want you to make sure that you can always interpret your graphs. Remember, you have different graphs that you're looking at. You must be able to interpret it, know and understand conceptually where it fits in. You must be able to apply the definition of rate of reaction to graphs. And remember, you also will link that up to the collision theory. That graphs will be linked to the collision theory on a sub-micro level, and that is where you will talk about more effective collisions per unit time, faster rate of reaction. So you need to bring that back and link it to the graphs. And obviously, for rates of reactions, you must try and always recall the factors that affect the rate. So there are 6 factors, and that brings us to the end of our session. Thank you so much.